Oh, I'm sorry, this is number 12. So toolbox, just a box, and it's in the bed of a truck. Now, here's the thing. The truck is traveling in the forwards direction, so that suggests that the toolbox is also traveling in the forwards direction. You guys understand what I'm saying? Now, here's the thing. The toolbox is not connected to the truck directly. It's connected by friction, right? The bed of the truck can apply a frictional force to the toolbox. Right now, the toolbox is moving forwards with the truck. If the truck stops, meaning if this portion of the vehicle, which is the bed of the truck, begins to stop, the only way the toolbox will stop is if a frictional force acts on the toolbox between the surface of the bed of the truck and the toolbox. That's the only way the toolbox stops. So there has to be a frictional force this way on the toolbox. If there isn't, the box just keeps going in a straight line. So if it's slippery and there's no frictional force, the truck bed stops, but the toolbox keeps sliding forwards. I think there's going to be a static frictional force between the toolbox and the bed of the truck. In fact, they tell me that there's a static coefficient of 0.65. So there will be friction, but there's a maximum. If it takes more force to stop the toolbox than friction can provide, then the box is going to slide. We need to stay within the parameters of friction. Now there's two other forces acting. There's weight and there's normal force. None of this, I think, is a surprise. I think these are the three forces acting on the box. Any question about these choices? Because these are the kind of choices you need to make. Yep. Again, the box is going to accelerate because we want it to stop. So net force in the x direction equals ma. Net force in the y direction equals 0. We just have friction in the x direction, and it doesn't matter to me at this point what direction is positive and what direction is negative. I just need a frictional force. I'll deal with what that force is going to do later. So I'm going to make to the right positive, and I'm going to make upwards positive. That means that friction, static friction, equals ma. Any question about that? All right. And normal equals mg. Anything weird here? All right. And we know that friction must be less than or equal to mu times the normal force. I'm going to preserve the inequality, which means I'm going to do my substitution into my inequality equation. So I'm going to put ma in for the static frictional force and mg in for the normal force, so that I get ma less than or equal to mu s mg. Cancel the m's. So my acceleration has to be less than or equal to 0.65 times 10. So the acceleration of the vehicle has to be less than or equal to 6.5 meters per second squared. I'm doing this to preserve the inequality. The truck can slow down with less acceleration than this, but it can't slow down with more acceleration than this. Now, have I done anything outside of our series of steps that we've discussed in class? Okay. Understand, the series of steps need to be automatic. Formulating these kinds of problems, that's hard. Coming to grips with the fact that the box does have to accelerate, that it's sticking to the truck, knowing that it's the friction that's doing that, that stuff is the hard part. But this part needs to be pretty automatic. Because once here, I have to decide whether I'm going to make this positive or negative, because this becomes a motion problem. Initial velocity, 30 meters per second. Final velocity is going to be 0. Acceleration is going to be 6.5 meters per second squared, and I'm looking for the distance that the truck can stop. So I would probably say if this is positive, then you should make this negative. That's all. Or you could decide to redo all of that and make something positive and negative based on what you want. but make a choice. This is the motion equation. Do I need to continue this problem, or is this enough? Okay. The problem changes and talks about making a turn. So do you want to talk about the turn problem too? Okay. So the turn problem, I'm going to do two quick pictures here to try and help me. So there's the bed of the truck, and the box is located in the bed of the truck. And the truck has to turn, so the path of the truck, something like that. The truck is still moving forwards at the speed that they gave us, which is 30 meters per second. So yeah, it's got to be friction. That's got to be the force that's likely going to cause this. So when I consider the forces acting on the box, frictional force this way, weight this way, normal force this way, all the same forces, correct? Nothing is different. In fact, this will be the exact same analysis as we had a moment before. Does everybody understand that? So I could redo everything. Net force in the x direction equals ma. So friction equals ma. And then net force in the y direction equals 0. So normal equals mg. And friction is less than or equal to mu s times the normal force. All still the same, with one difference. This acceleration is the centripetal acceleration. Right? This is the acceleration about changing direction. It's not the acceleration for speeding up or slowing down. So because this is the centripetal acceleration, I have a different formula I need to use for the centripetal acceleration. So my frictional force will be mv squared over r. Nothing else is different though, but that's a big difference. But my procedure will be the same. I still have a group of things that I got from Newton's laws. I'm going to see if I can figure out how to smash them all together to get what the problem asks, and the problem is asking about r. What's the radius of curvature? What is the tightest turn the truck can make without the crate sliding off the truck? So that's what we're going to do. I'm going to make the same substitution. M v squared over r is less than or equal to mu s times mg. Right, same substitution as before. I will point out quite clearly that it still doesn't matter what the mass of the toolbox is. And I need to kind of solve this for r. So I will multiply both sides by r. And don't forget some of your rules here. If I multiply both sides by r, you have to know if you're multiplying by a negative number, because if you are, that flips your inequality. Do you remember that? But the radius of curvature can't be negative. Does that kind of make sense? So I know, I'm confident that that's got to be a positive number. I just need r by itself, so r is going to be greater than or equal to mu s g over v squared. So I'm preserving the inequality, and I do that on purpose because it tells me something that you can't get any other way. It tells me the threshold. And in this case, oh, I guess I can't do algebra today. That should be v squared over mu sg there. Sorry, you should check my algebra. Preserving the inequality tells me that r can be this small and bigger, right? That's what greater than or equal to is. So if I want to find what the minimum turn is, then I set it equal to. But it tells me that I'm on the right side of this problem, that r can be a bigger number and that I have found what the minimum is. So I'm going to encourage you to continue to preserve the inequality in your problems when you can. It makes a difference. It also tells us how these are related. Obviously, if you make it stickier, r can be a smaller number because that makes the denominator get bigger. But if you're traveling faster, r is going to have to be a smaller number. It's going to have to be a bigger number. It makes perfect sense. You go faster, you're going to have to turn with less sharpness in order to make sure stuff in your car doesn't start moving around. So we're told that the record has a velocity of 33.3 RPM, rotations per minute. So we're going to have to probably make use of that. That means the bug is on a record. The whole record is spinning at 33.3 RPM. This is known as an angular speed, and we will be doing a whole unit on angular speed second semester. It's not much to ask about angular speeds, I think, here, but there are some things about angular speeds you need to know. And first, no matter where you are on the record, you are traveling at 33.3 RPM. Does everybody understand what that means? Because that doesn't mean that everybody on the record is traveling at the same linear speed. If we look at these two places on the record and say that this is the starting line, these two objects will go around and make it back to the starting line at the same moment. You guys understand that? Because they're all stuck to the record. The record goes 33.3 rotations per minute, so the time it takes for the record to go around is the same for both objects. So their angular speed is the same. But the thing on the inside, like there at the middle, compared to the thing on the outside, on the edge, they don't travel the same distance in that time. So the object that's on the edge has a faster linear speed than the object in the middle. You guys see why that has to be true? If not, think of it this way. It's 33.3 rotations every 60 seconds. A rotation is one circumference, correct? So a circumference is 2 pi r. That would now move it to meters. Do you see how if r is getting bigger, the radius, their linear speed is getting faster? So keep that in mind. This is how you calculate the linear speed of the bug. You're going to need that for later. And it's clear that the linear speed of the bug is related to how far away they are from the center. That's just the start of the problem, but it gets us started. The rest of this problem is exactly the same as the truck problem. So let's look at the truck problem the same way. We have, there has to be a force this way on the spider. That's got to be from static friction. The spider's got weight and normal force. Good to keep going? Net force in the x direction has to equal MAC. Net force in the y direction has to equal 0. Normal equals weight. And friction equals mv squared over r. We're going to have to get v from there. It's static friction that holds the bug in place. So static friction must be less than or equal to mu s times the normal force. This will be the same group of substitutions. So I'm going to sub in here. I'm going to sub in there. And that gives me m v squared over r must be less than or equal to mu s mg. Doesn't look like the mass of the bug matters. But you guys do see that this is the exact same question as the truck question, right? The truck going around the circle. So, and keep this in mind, anything that's going in a circle that requires friction to do so will be exactly the same as this. I think we want the coefficient though this time. We cancel the m's, and the coefficient of static friction must be greater than or equal to v squared over rg. We were told that r was 0.12 meters, and g, of course, 10 meters per second squared. You have to get v from 33.3 times 2 pi r over 60. All of that squared. This will tell you what mu s is. The rest of the problem is this exact thing just done in reverse, right? Do you guys understand what I mean by that? They give us a coefficient of friction, and they ask us to find the velocity, or they ask us to find the distance. It's the same problem, just you have 0.22 now for your coefficient of friction. And that's as far as you can go. But again, if you're trying to create a differential equation, we still start with a net force problem. We identify the forces that are acting in the system. We apply those forces in the x and y direction, set one of them equal to ma, one of them equal to 0. Nothing is different there. However, when it comes to creating a differential equation, you need to sub in a differential for one of your variables. We want velocity as a function of time. That's why we're subbing in dv dt and not dx dt for the velocity. We're trying to get it all in terms of one variable. This puts one variable in there, dv. Now, some of you have more advanced math skills. You should continue this problem. And for those of you who have those advanced math skills, I'm just going to get you set up. All right? The rest of you, we're going to do this second semester after we've gotten accomplished with this stuff. I'm not going to spend a lot of time on it first semester, okay? Splitting a differential means writing the differential separated. I just multiplying both sides by dt. That's the first step to splitting a differential. The second step is to collect variables. So anything with t in it has to be on the same side with dt, and anything with v in it has to be on the same side as dv. So you guys in calculus, you're eventually going to learn this, but, oh, this is squared still, sorry. So I'm going to divide both sides by v squared. So I've gotten everything with a v in it on the same side as dv, and everything with a t in it on the same side as dt, but there is no t. Now, this is the part that I'm kind of expecting you math people to be able to do. You integrate both sides. You're learning integration in calculus. We've done some integration in here, but again, I'm not going to go through all of this with you. But for those of you who are doing this, you have to set common limits. This is something you don't do in calculus, what we do here. I want you to set the fact that at time 0, the velocity is v naught. And we're looking for a function of v with respect to t. So I'm going to put v in the future and t in the future in the top. Now you just have to do your calculus. Now I say that knowing that there's a lot of algebra after this. There's just a bunch of algebra after this. But the actual calculus is relatively easy, and we did some of this already. We said things like this is t to the 0 power, and did the polynomial function. This we've talked about. We didn't do all the symbology, but we talked about it. We'll talk about it more second semester. If you can make it to here, though, that's usually good enough. What we have to do from here on, that gets you about one more point on the AP exam. They don't give you very many. And they usually tell you what the solution is. We'll learn how to do it, but I don't want to spend a lot of time on our homework doing it here. Math folks, you do this. That's v to the negative 2 power. It's a polynomial function. You can do it. All right. Anything else in the 1 minute left? So in the box in the back of the truck question, so this is for 6th period, so this is just the bed of the truck. I'm not going to draw the whole thing, but you get the idea that the truck and the box are both moving this direction at 30 meters per second. Now, how fast is the box going? Meters per second, that's right. Now, the truck is going to stop. That means if the toolbox wishes to stop too, as if the toolbox has any thoughts of its own, but if the toolbox is going to stop, something has to cause it to stop. That's it. What could possibly cause the toolbox to stop? Friction. It's the only force that could do so. In fact, looking at the picture I've drawn, The only way the toolbox can stop is if a force in this direction is applied to the toolbox. What force do we know about that's parallel to a surface? Friction's a good choice here, right? And I think you guys can probably put together in your head, if there's no friction, if the truck stops, the box just keeps going until it hits the front of the truck, and that stops it. But something has to push on it, and friction is a reasonable choice, partly because they said friction in the problem. Now, there's other forces acting on the box. None of them particularly unique. I'd say these are all the forces acting on the box. Any question about them? At this point, still trying to work the problem the way we've talked about, I'm going to make this the positive x direction and this the positive y direction. Net force in the x direction has to equal ma, and net force in the y direction has to equal 0. Anything weird here? Anything we've not done before? So friction equals ma, and normal equals mg. Anything weird here? All right, so this is what Newton's laws can do for us. Now, there's a few of you who still don't understand why I've done this, but I want you to understand something. Some people think that the box is stopped, but it is not stopped. It is stopped relative to the truck. I mean, the box and the truck travel at the same speed. So compared to the truck, the box isn't moving. But compared to the ground, is the box moving? Yes, and that's what we're talking about, compared to the ground. Now, we have a limit on how much friction is available to stop the box. These are all the things that are involved in this problem, but this is also all there is involved in this problem. So if I wish to find out the distance the driver of the truck can stop in, I think what I can do with this information is figure out the acceleration that the truck can stop in. And then using a motion equation, figure out the distance that the truck can stop in. We know that there are parameters, like the truck is moving at 30 meters per second, the final velocity of the truck is going to be 0. We are interested in making this as short as possible. We can only figure out what that distance will be if we know one more thing. And force could give us the acceleration, so it seems not unreasonable to use acceleration over there to figure out, use force over there to figure out what the acceleration would be. So I'm going to encourage you to do the problem the way we described it on Friday about subbing into the inequality. So that's what we're going to do, sub into the inequality. That'll give me ma is less than or equal to mu s times mg, cancel the m's, and my acceleration has to be less than or equal to mu s times g. That's it. So that sounds like it's got to be less than or equal to 6.5 meters per second squared. Now, be careful with your signs. We made to the left positive, or I made to the left positive. That would suggest that the truck's velocity right now is negative 30. But if you want, just reinterpret the problem. You can make the acceleration negative and the velocity positive. Whatever you do at this point, you're just looking for a relationship that can tell you how far the truck needs to stop. So I would encourage you to be cognizant and aware of what you're doing with direction, and you'll get your answer just fine. I don't think there's anything more I have to do on this problem, but I will work the kinematics equation if you need it. All right. Do you want to do part 2 of the problem where the truck is turning? All right. I think for part 2 of the problem, I'm going to take a slightly modified approach, and that I want to look top down on the box. So box in the middle of the truck, and I'm looking down. Is that okay? And we're told that the truck is trying to make a turn. Of course, keep in mind, the truck's traveling like 65 miles an hour, so I'm assuming we're talking about not like a left turn from one street to another, but perhaps an on-ramp or something like that, I would hope. If the box is going to stay traveling in a curved path, knowing that its current velocity is this way at 30 meters per second, there's going to have to be a force this way to cause the box to turn to the left. Question about that? All right. So reminding myself that this is still just a box resting in a truck, like so. I think we're still dealing with the same set of forces as before. A frictional force to the side, weight downwards, and normal force upwards. I don't think any of these forces are any different as long as the truck is still level. Any question about that? So net force equals MA in the X direction, and net force in the Y direction equals 0. Here's the change. This acceleration isn't speeding up or slowing down the box. It's causing the box to turn. So I'll put my centripetal acceleration marker in there to remind myself that this acceleration is based on how the truck turns, what it does while it's turning. So that means that my frictional force has to be equal to mv squared over r, while at the same time, normal equals mg. Yep.
Where does that equation come from, v squared over r?
Aside from the fact that I just stated it in class, like how would you find this? At this point, the problem is largely the exact same as before, right? I'm going to use this to kind of relate these variables together. So mv squared over r will be less than or equal to mu s mg. Cancel out the m's, and I'm going to solve this for r. So I get, let's see, r is greater than or equal to v squared over mu s times g. I like the fact that by using the inequality, we know that r is a minimum, that there's a finite minimum radius of curvature, so I can't turn any tighter than that minimum. Of course, I can make r greater. And I look at this side and I see things here that I think make sense. Like if I wanted to have a tighter turn, meaning if I want r to be able to be a smaller number, I would have to slow down, right? That has the biggest impact. But also, maybe put something in the back of the truck that makes the truck stickier for things, because if that went up, that would allow me to have a tighter turn as well. I'm not gonna be able to adjust gravity. So, all right. So it's 15 degrees with the horizontal. So this is related to a top-down view of the same thing, where the ball has a velocity in this direction. We don't know what it is, but it's traveling in a circle, and this is the string is 1.2 meters. I don't know what r is. Okay? Ready to begin? All right. The first thing I'm going to notice is that the net force on the ball in the y direction has to be equal to 0. I see two forces acting on the ball and only two forces acting on the ball. Let me go ahead and draw that so we have some commonality here. I think that there is a force of tension in that direction, and I think there's a force of weight in that direction. So this is mg, this is tension. At the same time, I think, is all that good?
Yes.
All right. So we're trying to figure out the velocity. I think one way to do that is just to analyze the forces. I think that'll get us there eventually. So net force in the x direction has to equal MAC, and net force in the y direction has to equal 0. That all good for you guys? So in the y direction, I get T sine 15 equals mg. And in the x direction, I have T cosine 15 equals mv squared over r. Any question about that? All right. I don't know what r is, but I have a way of calculating r. R is not 1.2. R would have to be, oops, that red line here. This is what R is. So it looks like R is 1.2 cosine 15 degrees. Everybody see where I got that from and why? I mean, it's going to be close to R, but if we're trying to, do the problem correctly, we should probably take this into account. Your lab, we're ignoring this, but here we're going to take it into account. Hopefully you spun the string fast enough. So we're looking for V. We don't have M. We don't have T. I think we're going to be able to eliminate some of this stuff. So the first thing I'm thinking about doing is kind of stacking those two and taking T sine 15, which equals mg, and dividing by T cosine 15, which equals mv squared over r. Whenever I see a sine over cosine like that, I like to see if there's a way for us to kind of eliminate it. And that's going to give me tangent 15 on the left side. It's going to cancel the m's and give me g r over v squared on the right side. Just doing arithmetic. I can do the steps more pronounced if you need them. Yep.
What is, oh, never mind. I forgot T over T is just one.
Yep. So is that all good so far? All right, so again, doing this, you don't have to do it this way. You could have just as easily solved this for T and substituted in over here. That works too. Either way, we're still trying to figure out V. I mean, our goal is V. So V squared equals GR over tan theta. Getting closer, but again, I can't have R in my answer, so V squared equals G times 1.2 cosine 15 divided by tangent 15. All right, now we've gotten someplace. We can do that, right? And this will give us V. So I'll leave that to you guys. Take the square root. That's how fast it's got to be going. Interestingly enough, it doesn't matter what you have on the end of the string, right? The mass canceled out. So you get the same velocity regardless, as long as you can make it 15 degrees. So whether you do this problem as the elevator or the person, the problem is exactly the same. So I was asked to do the elevator, I will do the elevator. If you want to repeat it, then just repeat it for the mass of the guy, and the tension force becomes a normal force. So this is 325 kilograms, the person and the elevator together. So, it's time to be real. So there are 3 steps to this problem. There's 2 meters per second for, did it say 1 second? The skydiver dumps out of the airplane. Yay. Their initial velocity is 0, but they are experiencing a drag force that is proportional to their velocity. All right. We talked a little bit about this problem already. We know that there's the potential for a steady state condition. I've not used the word steady state condition, but you'll hear it from time to time. Steady state means that you have a net force of 0. That condition is going to occur when you have fallen for a long enough period of time for the downward force of weight to be equal to the upward force of drag. And we talked about that in class. It ends up being mg minus kv equals 0. So this is known as terminal velocity, mg over k. Okay? I'm putting it out there because calculating terminal velocity is within your capabilities for this problem, and if it was squared, I think that's just fine. You should have no trouble with it. For us, it's the middle ground part. It's what it takes to go from having no velocity to having the terminal velocity. That's when you're accelerating. We're picking someplace in the middle. There are 2 forces acting on the guy. It's weight downwards And the drag force upwards, that's what the negative sign indicates, that the drag force is in the opposite direction of the velocity. So that'll give us mg minus kv equals ma. I've chosen to make downwards positive. I think that's nice and reasonable. This is your net force equation. Nothing weird yet. However, you're supposed to make a differential equation. You have a choice on how to do a differential equation. You either sub in dv dt for the acceleration, or you sub in dx dt for the velocity. Only one of those is the right thing to do here. You want everything in terms of one variable. So you're going to sub in for the acceleration dv dt. That makes everything in terms of velocity. If you subbed in for the velocity dx dt, you just replace one variable for another variable, but you still have acceleration and now position. That doesn't make it easier. So you want everything to be in terms of one variable. mg minus kv equals m dv dt. That's creating a differential equation. I expect that you can reach at this point. I expect you can figure out what terminal velocity is. I expect those things without any difficulty. And of course, this is a net force problem. I will expect you to do more. There is more to do here. And one of those is splitting a differential. That involves multiplying both sides by whatever the bottom of the differential is. This will be the next steps. Then collecting like terms, which means you collect everything that has t in it and you put it on the side with dt. And everything that has v in it, you put it on the side with dv. So that's going to be dt equals m over mg minus kv dv. These are the next steps. This is known as splitting the differential. And yeah, this is just algebra. Now, once you get here, yeah, you're probably done. You guys can't do the rest. Not right now. Some of you can. Now, any one of you who's in calculus should know that you can take the integral of both sides. That's what this is about. But in this class, there'll be a specific way I want you to set these integrals up. It has to do with making sure you link the initial conditions. We know at time zero, the velocity was 0. That's what they said in the problem. And we are looking for the velocity at some future time. So our top and bottom parts of our integral have to be linked up. Now, my suspicion is that some of you stopped paying attention because I said you wouldn't have to do this yet. And that's true, but you will have to do this. And you'll have to be able to put things like t to the 0 power here. Use the polynomial rule to find that this is t, evaluated from 0 to t. And you'll eventually have to do things like use substitution. And then use your u substitution to be able to do this integral. These are things you'll have to do in the future. I'm not going to make you do this now. You're barely wrapping your head around some algebra. But this is your future, and you'll have to be able to do these. Or you just don't get those points. But I think we can train for this. This is second semester kind of training. So I'm letting you So I believe we started talking about this problem on Friday. I don't know if we did it in every class or not, but I know we kind of set it up because I have pictures all over it in my notes. So I have this kind of ride. And the rider is stuck to the wall as the whole thing kind of spins. That good? All right. A quick top-down view. Come on. There we go. The ride is spinning, and the rider at this instant has a velocity in that direction. That is their tangential velocity. but they're going around in a circle. We call that their angular velocity. Them saying they want it in RPM is just them saying they want the angular velocity. In order for the person to successfully stay on this ride, they must be experiencing a centripetal force. Something has to be pushing that direction. Now, when I go through my series of steps to figure out the forces, I'm still going to use the same rules we've been using all year. Is there a conservative force acting on the person? Has to be, right? So, downward force of gravity. Are they in contact with any surface? Most certainly, they're touching the wall. Their back is against the wall. So although this is their weight, there's got to be a normal force this way. And I would expect this normal force to be plenty, probably greater than their weight. The reason I know that is because they experience a frictional force upwards. Right? Friction is going to oppose motion. The motion would be them sliding down the wall. So this would be the static frictional force. Now, this looks unbalanced to me. And so I'm going to make this the positive x direction and this the positive y direction. And so I'll have net force in the x direction equals MAC. They're traveling in a circular path. And the net force in the y direction equals 0. Any questions about that? Friction equals mv squared over r. Any question about that? All right. There should be, because I wrote this wrong to see if you're paying attention. And so when I asked if there's any question about it, if you're paying attention, what did I write wrong? Thank you. The force that's towards the center is the normal force. Gotta pay attention. Keep me honest. In the y direction, though, friction equals mg. Now, I'm going to do the same things we've been doing. I'm going to suggest that this is a static frictional problem. Static friction has to be less than or equal to mu times the normal force. I'm only writing it reverse because I have static friction on the right and normal force on the left, but it's still the same equation, right? And I'm still going to sub into my inequality. So now all we have is some algebra to work on. Looks like I have mu s times mv squared over r must be greater than or equal to mg. Well, the m's cancel out. That's good. Anybody can write it. All right, isn't that what that means? As long as your clothes aren't too slippery. So I guess I had to pick something on the inside of that wall that would be sticky enough that no matter what kind of fabric you're wearing, it provides enough friction. They usually use indoor-outdoor carpet. Who's ever been on one of the ones that's like this where the floor actually drops out? Only one of you? Yeah, it's indoor-outdoor carpet. Do you know why? You can hose it off. A lot of people vomit on this ride, so they want to make it clean. They just spin you fast enough or it'll stick to the wall. All right, this is largely the answer, but we want velocity. That's what they asked about. So I'm going to say that v squared has to be greater than or equal to gr divided by mu s. Now, here's where I want to kind of stop for a minute. Does this make sense? If I want to spin it, slower or faster, or all of these things in a location I think they should be, it seems like it's all pretty reasonable. The one that I'd point out the most is this one. If that number gets bigger, I can spin it slower. That means the surface is stickier, so I can spin it slower. That makes sense. Gravity gets bigger. Well, that's not particularly realistic, but I can imagine if gravity gets bigger, I'd have to spin it faster. So those are realistic things and make sense to me. You're supposed to get the velocity in terms of the angular speed. I'll remind you that when we did this, RPM is the circumference divided by the time. You see that's part of it, right? Now, rotations isn't in here. So the number of rotations, that's a different R. I don't want to put R there. So I'll write rotations. Per time, which was 60. If you want to find the answer to this, we set this equal to V when we talked about the bug problem. So rotations per minute has to be V divided by 2 pi R. Oops, I didn't put an equal sign there. Rotations over 60 has to be, V divided by 2 pi R. So you want to replace this, or you want to find this. So if you put this in for V and solve for rotations divided by 60, you're solving for RPM. But if you can get to this, that's fine. I hasten to do all of the steps because it just feels like it's a lot of overkill. There's some stuff about inclined planes I was desperately hoping you would just memorize. That doesn't seem to be the case much, but I would like you to. There are two forces acting on the box. There is a downward force for weight, and there's a force at an angle for the normal force. If I were to evaluate these forces, I'd probably make down the ramp my positive direction. And that means I'd have a positive y direction lined up with the normal force. There we go. And so this is positive x, this is positive y. Normal force is fine, but I'm gonna have to take the weight and break it up into components. Something like mg cosine theta and mg sine theta. Any questions? Alrighty. So the net force in the x direction equals ma, so mg sine theta equals ma, and the net force in the y direction equals 0, so normal equals mg cosine theta. There's no friction in part 1. I've done all of the force concept model I can. It says to me that A equals G sine theta. Now, we've asked for the angle of the ramp, but currently I can't get the angle of the ramp because I don't know what A is, even though I know what G is. But I do have information I could probably bring to bear in this problem. Things such as V naught is 0, V final is 5 meters per second, and displacement is 2 meters. I believe with this information, I can figure out what the acceleration of the box is. And if I figure out the acceleration of the box, I can figure out what the angle of the ramp is. So let's go with 5 squared minus 0 squared equals 2a times 2. That looks like 25 over 4 equals the acceleration. So that's enough for you to figure out what the angle is?
Yes.
Keep going?
No, it's
That enough? And you know how to do the rest of it? Right, because there's 2 more parts. You're supposed to find the frictional force, assuming the box slides down the ramp at a constant velocity after static friction is done, and then find the coefficient of friction. You want me to keep? Sure. So once we have the angle of the ramp, which I don't know what the angle is, you'd have to tell me, but does somebody have it already because you did number 4? Yes, sir?
It's 30.682.
13.682, so 13.7 degrees.
38.
Oh, 38, sorry. 38.7 degrees. So once we have that, the problem changes because we now have a frictional force. We're told that we break static friction, but we have a frictional force that allows the box to slide down the ramp at a constant velocity. We don't know what that velocity is, but it doesn't matter. As soon as it says constant, it says this is 0. That means that I need to reassess all the stuff in the x direction. First, mg sine theta minus friction equals 0. So friction equals m times 10 sine 38.7 degrees. I don't know what m is, so I can't get a better description for friction, but I know that normal force equals m times 10 times the cosine of 38.7. And since mu is friction divided by the normal force, friction divided by the normal force equals, looks like tangent 38.7, and that has to equal mu. That good? Excellent. So I didn't record any of that. Batmobile problem. There it is. Hit pause. So this is the setup for number 14. That all good? All right. I'm going to look at this from the standpoint of force because that's what we have. Net force in the x direction is going to be MAC, and net force in the y direction equals 0. I'm going to make this the positive x direction and this the positive y direction. I only see one component of the force in the x direction and a component of the force in the y direction. So this will be t cosine 25, and this will be t sine 25. All good? So t sine 25 equals MAC, and t cosine 25 equals mg. All good there? There's a lot of directions I could go or order of events, but I want to remind you that t sine 25 equals mv squared over r. And we're interested in finding the velocity and the time for one revolution. So we want v. That's going to make the difference. So I want to isolate v. One way to get rid of things that we don't have, like we don't have the tension and we don't have the mass. So I'm thinking we could probably get rid of that by writing this as t sine 25 divided by t cosine 25 equals mv squared over r divided by mg. All right, this will get rid of the t and get rid of the m's. So tangent of 25 equals v squared over gr. All good? Solve it for v. And I get v squared equals tangent 25 times g times L sine 25. Now this is the algebra, but you have values to put here. So tan 25 times 10 times 1.2 sine 25. Then take the root. This will give you the velocity. Oh, it's not 1.2. Sorry, it's 20 centimeters. 0.2. All right, once you get the velocity, the velocity equals 2 pi r divided by t, the period. One rotation divided by the time it takes to go around a circle. So period equals 2 pi r over v. I figured you guys had this from the lab, so I thought you could draw it into this problem. But if not, that's where it comes from. So you can figure out the period, how long it takes to go around in a circle just by doing that. And you people who had physics before, if you do this symbolically, you'll find out this comes out to be the same as a pendulum of the same length. And you'll see, you'll get L in there, but you do have to make the assumption that theta equals sine theta for small angles to see that. But that's from people who had physics last year. There's a conversation about that. I'm taking this equation, well, this one, and just dividing both sides of that equation by the same thing. So I'm taking, here, I'll say it differently. I'm really doing this. I'm saying t equals mg divided by cosine 25. Then taking this and plugging it in for t here. That's kind of what I'm doing. I'm just doing it all in one step. what I'm really doing is I'm dividing this equation by this equation. Does that make sense? Okay. I'm just noticing that I have m's on both sides and t's on both sides. So lining those up allows me to cancel out the t's and the m's in a single step. All right. So just listening to the problem, I have a plane that can develop a lift force that is proportional to the velocity of the plane. I'm just saying out loud the math sentence that they're saying there, right? The plane has a mass of 600 kilograms and a net force of 0 when V equals 180 meters per second. All good? That's the information from the problem. Well, mg and force of lift have to be in balance. I don't care about the thrust and the drag. Those are the horizontal ones. All I care about is the up and down ones. So I know the force of lift has to equal mg when we're at stable flight, which means kv has to equal mg. So that's k times 180 equals 6,000. This has to be my proportionality constant. So now, once I have that, and you can work out the numbers, we want the plane to have an upwards acceleration of 2 meters per second squared. So I want the lift force minus mg to equal ma, where a is 2. So this is going to be kv minus mg equals ma. So kv equals mg plus ma. I have a value for k, and I know everything else. So this will be 600 times 10 plus 2 times 180 over 6,000. Is that good? Now I'll give you the velocity of the plane to accelerate upwards of 2 meters per second squared. It's 600 times 10 plus 600 times 2. Right? Okay. That's good? Okay. Anyways, but I did this one earlier today, so I did record that one. I didn't record it this time, but I did it earlier.